Yeah, I want to thank you for the invitation. I will talk about eigenvalues distributions of sparse random graphs. So this is a joint work with Antti, Roland, and Yao. He's my advisor. So for the talk, I will concentrate on the random d-regular graphs. Usually we denote it by GND. But I will also compare some of the results for Erdős-Rényi graph. So for the random d-regular graph GND, it's just a uniform distribution on those simple d-regular graphs on n vertices. You just randomly pick one of them. And this is an example of a three-regular graph on 40 vertices. And you can see each vertex has a degree 3.
Is it Ramanujan, that graph?
I think so.
Yeah,
This is from your paper, what's an expander?
we know the biggest three regular planar Ramanujan graph we know is about 84.
Oh.
It can't be more than 300 by theorem.
Oh, so this is planar. Yeah, for a random d-regular graph, we will denote the graph by its adjacency matrix, it's A. So just the Aij, it equals 1, if and only if there's an edge between vertex I and J. Because those graphs, they are d-regular, so for the matrix A, each row has d non-zero entries, as the same as each column. So it has a trivial eigenvector, just 1, 1, 1, 1, 1, which gives the eigenvalue d. And besides this, there are two cases. Either the graph is non-bipartite, so all except for the largest eigenvalue, all the other eigenvalues are strictly smaller than d. But if the graph is bipartite, then it has another trivial eigenvector which takes the value 1 in one part and the value minus 1 in another part. It gives the eigenvalue minus d. And besides those largest one and smallest one, all the other eigenvalues are between strictly smaller than d. And in my setting, I will normalize those matrix A by a factor square root d minus 1. So H is A over square root d minus 1. In this normalization, it turns out, except for those extreme eigenvalues, all the other eigenvalues are on the interval roughly from -2 to 2. And we denote the eigenvalues of H from lambda 1 to lambda n. And in this rescaling, lambda 1 is just d over square root d minus 1. And the empirical eigenvalue distributions of those random d-regular graphs, they converge to the Kenstin-McCain distribution. So this is the empirical eigenvalue distribution. And the Kenstin-McCain distribution is just some factor dependent on d. And this factor it's a semicircle from -2 to 2. And here's a simulation for random 4-regular graphs with 1,000 vertices. As you can see, the histogram of the eigenvalue matches pretty well with this red curve, which is a Kenstin-McCain distribution. And also, this is just the extreme eigenvalue correspond to the degree d. And all the other eigenvalues, you can see it's just on the interval from -2 to 2. And this Kenstin-McCain distribution was first obtained by Kenstin. He computed the spectral distribution of the infinite d-regular tree. And later, for random d-regular graphs, this was proven by McKee. The method is a moment method. So if you have the adjacency matrix H, you can compute the case moment and takes its trees and maybe normalize it by 1 over n. Then this quantity is just 1 over n, sum of those eigenvalue to the power k. So you can think this is just the case moment of the empirical measure. So this, if you have all those moments, it characterizes the Kenstin-McCain distribution. And another way to view this quantity, you can expand the matrix H to the power k, and then explicitly it's just the sum of hi1, i2, hi2, i3, until hik, i1. So here is the sum over all the paths I1, I2 until ik. So as you can see, this quantity it's non-zero if at only it forms a path from vertex I1 back to itself of length k. And So for random irregular graph, it turns out for any vertex I, most of the vertex, it has a tree neighborhood of size log n. So to count, if k is smaller than log n, so to count this kind of closed path is the same as counting the path in the infinite irregular tree. So this you can replace this quantity by the path in infinite irregular tree. So asymptotically, the spectral measure should be the same.
Can you get corrections to it coming from the fact that you've got loops in general?
Yes, I think soon I will mention actually there. But the problem is it's possible you have some triangles and some small loops. Yeah, if you.
The few small loops
Yeah.
in a random graph, that's part of the proof.
That's true.
Yeah, it turns out actually for irregular graph there are not many small loops. So actually, the two I think if you just compute this quantity, the error is of order 1/n. It's pretty small. And here are more examples of those Kinston-McCain distribution. The red curve is d equals 3, and the green one is d equals 5, and the blue one is d equals 8, and the black one is d is 200. As you can see, when d gets very large, it becomes very close to the semicircle. You can directly see it from this expression. If d goes to infinity, it just converges to 1. So only thing left is the semicircle distribution. Also, the question I want to study is not about the whole spectra. I mainly concentrate on the quantities like the extreme eigenvalues. For the first eigenvalue, it's trivial, it's just a degree. So in other words, we are interested in the largest second eigenvalue. And those quantities, it's usually related to the collectivity of a graph. So here is a definition for the edge expansion constant. So given a graph G on n vertices, the edge expansion constant Hg is defined as a minimum over all the possible set S. So it's the boundary edges of the set S over the size of the set S. So among all the set S, which has maybe less than n over 2 vertices. So if this Hg, if it's bigger than some constant, then if you want to break down the graph into two disconnected components, you need to remove many edges. As the number of edges you need to remove is proportional to the Hg times the smaller component. And if you think for random for irregular graph, each vertex it has d labels. So all the labels they look the same. The radius 1 label is somehow similar to the definition of a manifold. Each vertex has some neighborhood which is similar to Rn. You can think this is some discretization analog for manifolds. If you think it this way, then this is exactly the Cheeger's constant. Just you take any set. This is the boundary volume over the volume of the set.
Would it be a manifold negative curvature, or?
You can Cheeger's constant. You can start it for any remaining manifold. Yeah. And for example, like this graph in Professor Salak's paper, I think the set S is the minimum is achieved for this set, and the Cheeger's constant for this graph is 1/4, something like that. But in practice, to compute the Cheeger's constant for given graph, it's a hard problem. I think it's NP complete. But thanks to this theorem by Tanner, Allen, and Millman, so if G is a de-Rieger graph on n vertices, then there's some universal constant, probably not dependent on D, small cd, such that the Cheeger's constant is lower bounded by the gap between the first and second eigenvalue. I think it's usually called the spectral gap, and upper bounded by square root of lambda 1 minus lambda 2. So basically, the Cheeger's constant is of the same order as the spectral gap. So come back to the for regular graph. As you can see, the spectral gap it has a pretty large spectral gap. So we know the Cheeger's constant it's something of order 1. So it turns out for all those random graphs, they have a pretty nice collectivity property. It's hard to break them down into two disconnected components. Okay, so as I mentioned, the compute the Cheeger's constant is NP hard, but compute the spectral gap, you just need to compute those two eigenvalues, which is much more tractable. And so to find a graph which has a very large Cheeger's constant, which is very robust, maybe you can try to find those graphs with a large spectral gap. And it's natural to ask what's the largest possible spectral gap for a d-regular graph. So this question is answered by Allen and Bapana. They showed for every collected d-regular graph G, there's some universal constant CD. The lambda 2 is at least 2 minus CD over the diameter of the graph G. And for a d-regular graph, on n vertices, the diameter is at least log n. Because if you look at any one vertex and look at the radius r neighborhood of it, it has roughly d to the r vertices. So for it to cover the whole graph, you need r to be at least log n. So the diameter of the d-regular graph is at least of order log n. So in this way, if we have a sequence of d-regular graphs on n vertices, then the diameter, it will goes to infinite. So the lim inf of lambda 2 is at least 2. So the largest spectral gap we expect is at most lambda 1 minus 2. So because of this reason, in a very influential paper by Lubatsky, Phillips, and Professor Salak, they coined the name Ramanujan graph. So a d-regular graph on n vertices is called a Ramanujan graph. If all those non-trivial eigenvalues, the absolute value is less or equal than 2. So again, there are two cases. If the graph is not bipartite, this just requires all the eigenvalues except for the largest one is less or equal than 2. If the graph is bipartite, then it requires all except for the largest and the smallest eigenvalue, all the other eigenvalues are less or equal than 2. And in the paper, they construct many of those Ramanujan graphs. So they take P and Q to be unequal primes, which equal 1 mod 4. And they give explicit construction of Ramanujan graphs as Cayley graphs of the projective linear group, the 2 by 2 matrix, each entry is in FQ, as the D is given by P plus 1. I think in the proof, essentially, they can compute for those Cayley graph. You can essentially compute any moment for any k, and this quantity is given by the solution of a certain quadratic equation. And the solution of those quadratic equations, they are given by Ramanujan's conjecture. That's why you call them Ramanujan graphs. And this result is only for the degree D is some prime to 1. It's natural to ask, are there Ramanujan graphs for other degrees? And this question, it was recently answered by Marcus Spielmann at Sravastava in 2013. They proved that, in fact, there exist infinite families of bipartite d-regular Ramanujan graphs. And their proof uses the interlacing polynomials. And in fact, the proof is pretty cute. They actually show that if you have a bipartite Ramanujan graph, then you can do a two-lift of the graph. Basically, if, for example, if you have this graph, then you do a two-lift. You lift each vertex to 2 vertex. At each edge, there are 2 ways to lift it. Either it's this way or this way. Like, for example, this you lift this way, this you lift it this way, and this you lift it this way. Then you get some graph with twice as many vertices as a base graph. And their proof, it goes like this. If you have a bipartite d-regular Ramanujan graph, then among all those 2 lifts of the graph, at least one of them is still a Ramanujan graph. So in this way, if you start from a trivial Ramanujan graph, like the complete graph d vertices, by repeating lift it, you get an infinite family of those d-regular graphs.
By the way, there is one feature in common in these two. I mean, we use Ramanujan, which in turn uses the Riemann hypothesis for curves over finite fields, and they use Lieb-Heilmann or
Oh, yeah.
on a circle. That's the common input in both proofs. So they both. So it's not just interlacing polynomials. It's this Lee-Yang theorem.
Oh yeah, I think the expectation of their
Yeah, that's a matching polynomial which has all its roots on a circle, and the Riemann hypothesis also puts all the roots on a circle.
Oh, I see.
And they both used it a critical point.
Oh,
There's something common to both.
I see. Yeah, thank you for the comment.
So you use what, Peter?
We use the Riemann hypothesis of Andre Bay.
Oh, but
And the proof of the Ramanujan conjecture.
Function field case.
Function, right, in the function. Yeah, that's what's the theorem.
Is the graph
Otherwise
zeta
you don't
function
have
of any use for that?
What?
Is the graph zeta function?
The graph zeta function is interpreted in, you can interpret the graph zeta function as a zeta function of a curve over a finite field. This is what, through the whole construction. And then the sledgehammer, the critical moment, is phase proof of the Riemann. But I'm just saying that it's not just interlacing polynomials. Many people say that. It also uses, they actually use Hellman-Lee.
Yeah.
Is the official thing.
So it's a Riemann hypothesis for graphs.
Sort of, yeah. For the matching point.
Yeah, but from the numerical simulation, it's observed that the distribution of the second largest eigenvalue and the smallest eigenvalue, they are well modeled by the so-called Tracy-Widom beta equals 1 distribution, so which are the asymptotic distribution for the largest eigenvalue of a Gaussian orthogonal ensemble. So for those of you who are not familiar with this, let me just quickly guide you through it. So the Gaussian orthogonal ensemble is just a n by n symmetric matrix. Each entry is a Gaussian, they all have mean 0 at the variance. The diagonal entries has a variance 2 over n. Off-diagonal entries has a variance 1 over n. The variances are chosen in this way, such that the law of the matrix, it does not change if you conjugate the matrix by an orthogonal matrix. So that's why it's called the Gaussian orthogonal ensemble. So if you plot the eigenvalue distribution of this guy, you get a perfect semicircle supported from -2 to 2. And then if you take out the largest eigenvalue or the smallest eigenvalue, it turns out they converges to the Tracy-Widom beta equals 1 distribution. Take out the largest eigenvalue lambda 1 and subtract 2 and rescale it by n to the 2/3. It converges to the Tracy-Widom distribution. Here's a plot for the Tracy-Widom distribution. As you can see, it's very similar to the normal distribution. You can hardly see the difference. But the only difference is it actually is a distribution, by this definition, it tilts towards the negative axis. And it turns out this Tracy-Widom beta equals 1 distribution is pretty universal. So the matrix I mentioned, each entry it has Gaussian, but it turns out you can replace those Gaussian to any distribution you want, like the discrete distribution, like Bernoulli. As long as the mean is 0 and the variance is 1 over n, you always get the Tracy-Widom distribution. This was the first proof by Soshnikov for the distributions, entry distributions which are symmetric, and then proved by Tao and Wu. And finally, some necessary and sufficient conditions was discovered by Li and Ying. Basically, as long as those entries has a bounded force moment, then the largest eigenvalue will have the Tracy-Widom distribution. So because this Tracy-Widom is so universal, based on the numerical simulation by Miner, Lovikov, and Sabali, they just based on their simulation, they conjecture that for random Dirichlet graph with n vertices, you do the same thing for the second largest eigenvalue lambda 2 minus 2 times n to the 2/3. It converges to the Tracy-Widom distribution. And the same statement holds for the smallest eigenvalue. This is their conjecture. But according to Professor Salak, actually, some more careful simulation indicates there should be some shift for the Tracy-Widom distribution. The shift should depend on D. It's quite delicate. But if you believe if you believe this conjecture, like C, for example, if the CT equals 0, because the Tracy-Widom distribution, it biased towards the negative axis. So for this lambda 2, you roughly have like a 54% of the chance it will be less or equal than 2. And for the smallest eigenvalue, you also roughly have 54% of the chance it's bigger than -2. And because of the second largest one and the smallest one, they are asymptotically independent. So roughly, if this is true, you will have like 27% of those irregular graphs. They are all Ramanujan graphs. So in fact, if this is true, there should be a lot of Ramanujan graphs.
But even if CD is not 0, then
yeah, even CD is not 0, you still have some positive proportion.
I think the numerical evidence, which is maybe a bit shocking, is it's not 100%. I have a bet with no galon. I wanted the Ramanujan is special, and he wants it to be always true. It's certainly not always true. So it's not 100%. But apparently, he's probably more right than I.
So you believe that there's a fraction then?
Yeah, based on the numerics of these guys. Yes.
So 27 is numerical, or is it estimate based on?
No, so they did the numerics, and the Tracy-Widom is coming from, the prediction is coming from the bias in the Tracy-Widom. It's not
Yeah,
Bias CD is numerical, or is it theory?
they see the bias.
Yeah.
If you got, he went up to a few hundred, and
yeah.
you have to go quite high to make it on Ramanujan graph already. So it starts off like at 90% or Ramanujan, then you increase and it starts dropping. The question is, does it drop to 0 or stop at 27%?
Yeah, this is for finite D.
Of course, he's coming to what he can do.
Yeah, that's why I asked.
I think he's leading up to it. This is all.
Yeah, this is all for finite D. Roughly the heuristic, this is 54, then this will be.
What you can prove, yeah.
Yeah, so yeah, this is a pretty hard conjecture, but if you are not that strict, you don't require the eigenvalues are strictly less than 2, then much is known. So here's the theorem by Friedman in 2004 at the bottom of the original proof is more than 100 pages, and a new proof was discovered by Botinov in 2015. So they prove that if G is a random de-Rieger graph on n vertices, then with high probability, all those non-trivial eigenvalues are bounded by 2 plus little 1. So that little 1, they can take it to be like a log n over log n.
It was conjectured by Alon.
Yeah.
And proved what I like about the subject in combinatorics. Alon refuses to read papers that are more than 20 pages. So even though his conjecture was solved, he said it was too long. And how many pages is Mr. Bohr? I don't know.
I think 40 pages, still longer than his 20.
It's 40 pages instead of
Yeah.
Anyway, that's called the Alon conjecture.
Yeah, and yeah, but there are proof only for D is fixed. It actually does not work for D also goes to infinite. So when Wu made this conjecture, even for D less or equal than n over 2, so both D and n goes to infinite. So here, this may not be something serious. If you can consider for D regular graph, you can consider the complement of it. Then it's n minus D regular graph. And in this way, actually, this can be extended for any D. So he conjecture for any, even in this regime, D and n both goes to infinite. The maximum of the non-extreme eigenvalue is still 2 plus little 1 times the factor square root 1 minus D over n. So if D is a constant, then the last term is basically 1. So it goes back to that theorem. And the reason their argument, because intuitively you should think if the graph is sparser, the problem should be harder. But the reason their argument does not work in this case is because more or less this argument is a moment method. So basically, they try to compute this moment for k large. K is much bigger than log n. So if k is much bigger than log n, then for this sum, then you have the largest eigenvalue, which is d over square root d minus 1 to the power k. And for the sum of the rest of the eigenvalues, asymptotically, it's just the maximum of lambda 2 and lambda n absolute value, this plus some little 1 to the power k. So if k is much bigger than log n, you have the sum is given by this expression. So if you can control the case moment, k is much bigger than log n, then you can have the bounds for lambda 2 and lambda n. But their argument is this moment method as reduced to counting of those paths. Because for the random irregular graph, for most of the vertices, it has a log n neighborhood, which is a tree. Although that is not much bigger than log n, they are able to develop some sophisticated way to compute this moment. But if d also goes to infinite, like if d is n to some epsilon, then the radius of the graph is only some constant. So in this setting, to compute those moments, it's much harder. Yeah, but there are many some results on the at least for the bounds for the lambda 2 and lambda n. So they can show that lambda maximum of lambda 2 and lambda n is of order 1. It does not grow with d. This was first given by Han and Zemeridi. I think they can prove it up to d is like square root n, and then by Cook, Goldson, and Johnson, they can prove it for d is much smaller than n to the 2/3. And finally, they can show it for any d less or equal than n over 2. And,
so when you say it was proven, you mean the Vu conjecture?
No, this is they only show this is of order 1. They didn't see the constant 2. But at least it does not grow with d or n. Yes, the main result I will talk about is just to try to understand those kind of questions, but only for in the regime both d also goes to infinite with the size of the graph. So the first result is with Roland and T and Yao. We can show that if this d is much bigger than 1 and much smaller than n to the 2/3, the maximum of lambda 2 and all the non-trivial eigenvalues, they are of order 2 plus little 1. And we have the explicit form for the error. It's given by 1 over d cubed plus 1 over n to the 2/3 plus d squared over n to the 4 over 3. And
You don't know the sign of those coefficients, I guess, right?
oh,
I mean,
what do you mean sign?
the sign. In other words, you don't know there's less than 2 or not.
No, we don't know. No, we don't know if it's less than 2. I don't think it's less than 2.
You go to infinity arbitrarily slowly and get.
Yeah.
Yeah.
Yeah, I think this error term, we need d to be d go to infinite to have this to be of little 1. Yeah, and also this strange upper bound is because we want this term to go to 0. So we have d to the n to the 2/3, but the goal is to understand very, very sparse graph, so we didn't push too much for the non-sparse regime. And the second one is we can show that at least in this regime, d is much bigger than n to the 2 over lie and much smaller than n to the 1/3. Actually, lambda 2 subtracted 2 and rescale it by n to the 2/3, it converges to the Tracy-Widom distribution. Because of this statement, to show this statement, you really need that the fluctuation of lambda 2 around 2 is of order n to the minus 2/3, because this implies that. So for our error this error to be smaller than n to the minus 2/3, like for the first term to be much smaller than n to the minus 2/3, we need a lower bound for d. That's why we can only do it for d is much bigger than n to the 2 over lie. And for the last term to be much smaller than n to the 2/3, we need that the d is much smaller than n to the 1/3.
You converge to the Tracy-Widom with the exact offset that they have, the exact number they have in their definition of that distribution.
Yeah, yeah. This is exact.
That's remarkable.
Yeah. But I guess
from a certain correction in their problem. It's like saying that the Gaussian has a built-in.
Yeah, because that's Tracy-Widom is it's not does not have mean zero. Yeah, but I guess because it must be the U conjecture that's a shift to CD.
I'm nervous about that.
It goes to 0 if D is large. But anyway, so this will still give you, we can, if we want to, we can rephrase this like in this way: if D is large enough, and we take n in the range from D cubed to D to the 9/2, then among all.
Can you remind me something in the longest increasing subsequence where it's also fluctuating to Tracy-Widom? It's also with the exact same. It's the same offset. So maybe it's obviously very natural, because that's a completely different problem seemingly.
Oh, so what's the
The longest increasing.
Oh, that.
Yeah.
Yeah.
Usually in these problems, there's a correction term that's built into the asymptotic. You sort of work out the main term, and then you say the fluctuation. And the issue is whether, and what I'm finding, what I'm concerned about is that the correction term in the fluctuation built into in their model, which was just a random matrix theory, not sparse.
Yeah.
Right?
The
In all these
Tracy-Widom.
cases, it's exactly the Tracy-Widom. So the question is, Tracy-Widom should come with parameters, like it's a Gaussian with mean zero variance something.
Yeah, I think, in all those examples, you just subtract some number which does not depend on n. Then you get the Tracy-Widom.
Is this subtraction related to the fact that in some of these problems there is a trivial eigenvalue which recurs, and others you don't have that?
I don't know. In the random matrix thing, there isn't a trivial.
Exactly. So would that make a difference?
Yeah, it could be.
Yeah, but
By the
then
way,
we can't
there
continue.
is an eigenvalue out here far away, which might be doing some repairing. You're right.
I see. Yeah, although this does not give an infinite family of Ramanujan graphs, it does give you a lot of those graphs. Yeah. So before I'm going to the proof ingredients for the proof of this theorem, let me just quickly mention some results for the Erdős-Rényi graph for comparing. So the Erdős-Rényi graph we denoted by GNP. So it's a graph on n vertices, and each edge is picked with probability p. So in average, each vertex will roughly have the degree p times n. You should think this p times n is a d in the d-regular graph. So first, if the average degree is bigger than n to the 2/9, it's proven by Erdős, Antti, Yao, and Ying. The largest eigenvalue, subtract 2 and rescale it, you get a Tracy-Widom distribution. And later, this was pushed forward to the sparser regime if the average degree is bigger than n to the 1/3. And you still have the Tracy-Widom distribution. But this time, you need to subtract something which is 2 plus 1/n times p. So there's some correction term. Then you still get the Tracy-Widom distribution. Yeah. The sparsity somehow it shifts the edge a little bit. So this time, this quantity does depend on n. And later we show with Ben and Yao, if you go to even sparser regime, if average degree is much smaller than n to the 1/3, but still bigger than n to the 2/9, then the second largest eigenvalue is no longer Tracy-Widom. This time it's given by a Gaussian distribution. And you subtract some E star, which depends on the average degree, and rescale it by square root p times n. This gives you the Gaussian distribution. And we can explicitly identify the fluctuation. It turns out the fluctuation is given by the fluctuation of the total number of the edges. And you can think this result like if there are, for the second largest eigenvalue, there are two sources of the randomness. One is from the matrix structure, the Tracy-Widom fluctuation. Another is from the total number of the edges. As the two sources of the fluctuations, they compete with each other. When the graph is not very sparse, the fluctuation for the total number of edges is small, so you can only see the Tracy-Widom distribution. When the graph gets too sparse, then the fluctuation of the total number of edges is big, so you see the Gaussian distribution. And the interesting phenomenon is that the critical exponent 1/3. Then in this in this setting, the two sources of the randomness, they are of the same order. So you see the lambda 2 is a combination of the Tracy-Widom distribution and the Gaussian distribution. Yeah, so far, any question? Okay,
Are
now.
these theorems harder than the universality, the old, well, by now old, universality for the spacing in the bulk?
Oh, I think it's.
Do you have the same technique?
Yeah, the technique is slightly different. So at the edge, to get the universality, you need to know the location of the eigenvalue in, up to the order n to the minus 2/3. But in the bulk, actually, you don't need to know the distribution or the precise location of the eigenvalue. So for example, the bulk universality for those Erdős-Rényi graph is true. It's true all the way as long as the average degree is bigger than n to the epsilon.
Tracy-Widom comes from some determinant signed by some process. In the universality that Schlein, Yao, and Koku, they never compute the answer. They only show it's the same
Yeah.
as what you would do in the Gaussian, and then so it's, but they don't give a new computation of that answer. So this.
Yes, for those we still compare with the Gaussian. Yeah, because after all, the hardest part to prove those Tracy-Widom is harder than the proof with central limit theorem is because they are not, for central limit theorem, there are many ways to characterize a Gaussian. But for Tracy-Widom, the only thing we know how to get a Tracy-Widom is by the Friedman determinant, those explicit computation. So that's the hardest part. If there's some other way to characterize a Tracy-Widom, maybe we can understand this phenomenon better. So the proof. So for the proof ingredient, so here A is an adjacency matrix and H is a normalized version. So you can think H is just some self-adjoint operator. So to understand the spectral of the self-adjoint operator, the quantity really the quantity is the Green's function of the operator. So the fundamental object we use to study the spectral of the adjacency matrix is the Green's function GZ, which is just H minus Z inverse. And Z is some complex number in the upper half plane. And also the Stieltjes transform of the empirical measure. So MZ is just 1 over n times the trace of the Green's function. Explicitly, it's just 1 over n times the sum of 1 over lambda I minus Z. The Stieltjes transform, it contains all the information of those eigenvalues. As a Green's function, it contains both the information of the eigenvalue and the eigenvector. So in general, you can define the Stieltjes transform of any measure rho. So just as rho x over x minus z. So it turns out the Stieltjes transform, it contains all the information of the measure rho. You just look at its imaginary part. I take z to be e plus I eta, and since the eta goes to the real axis, then you recover the measure rho e. If there's no density, just interpret this as in the weak sense. And for all those distributions we find from the random matrix setting, it turns out all their Stieltjes transform of those measures have a very nice form. Like for the semicircle distribution, the Stieltjes transform M semicircle, it satisfies this quadratic equation m squared plus zm plus 1 equals 0. And also for the Kestin-McCain distribution rho d, the Stieltjes transform md, it can be written in terms of the M semicircle just by 1 over minus z minus d over d minus 1 M semicircle.
When you're making statements like that, you have to keep z a little bit away from the real axis, right? Or away from the eigenvalues?
Yeah, actually, if you first you can define, compute the Stieltjes transform for the upper half plane, then you can analytically extend it.
For a graph, it's not.
No, I get the eigenvalues though.
Yeah, but I'm just saying, man, analytic continuations.
Oh, this is just for the semicircle distribution. There's no eigenvalue. Yeah, and for this one, you can also solve for MC and plug in here. Then you get some self-consistent equation for MD only. And the Stieltjes transform, now if you look at for the empirical eigenvalue, it also contains the information. If you look at the imaginary part of M, so it's just imaginary part of 1 over n times sum over 1 over lambda I minus z. The imaginary part of this guy is just imaginary part of z, which is eta over the lambda I minus z square. So it's lambda I minus e square plus eta square. So this quantity is just the empirical measure convolution with the Cauchy distribution on the scale eta. So it's the same as just look at the spectral and then you zoom in on the scale of eta. So this eta is also called the spectral resolution. So if you want to understand the spectral on the scale of eta, then you just need to understand the imaginary part of the Stieltjes transform at e plus I eta on that horizontal line. So we can use the Stieltjes transform to detect the locations of those extreme eigenvalues. Like if you take z to be lambda j plus I eta, then you look at the imaginary part of mz, then you can just the sum correspond to terms, which is I is not j, and if I is j, then lambda I minus z is just eta, so it gives you the extra term 1 over n eta. So if there's an eigenvalue at lambda j, then it will have a contribution to the imaginary part of the Stieltjes transform of number 1 over n eta. So if you can underestimate the imaginary part of mz up to the precision 1 over n eta, then you can use it to detect if there's really eigenvalue at lambda j. Basically, if you can understand this imaginary part of mz at e plus I eta at the precision up to 1 over n eta, then you can see in a small window next to E if there's an eigenvalue or not. So
you never told us what random model of graphs you use.
Oh, random graph model, which is the uniform one. Uniform measure.
Measure in the regular one.
Yeah, uniform measure on the regular one. So here.
It's hard to work with, so you really
Yeah.
work with that.
Yeah, so here's a toy example. I can quickly show you how to compute the Stieltjes transform of that Gaussian orthogonal ensemble. So in this case, we want to show that the empirical measure converge to the semicircle distribution. So that we want the mz to be very close to this M semicircle. And we know that M semicircle it satisfies this quadratic equation m squared plus dm plus 1 equals 0. So to show m is close to M semicircle, what we will try to do is to show that m also satisfies this equation. Then by take difference, we know that m is very close to M semicircle. So we denote the Green's function by h, which is Green's function by g, which is h minus z inverse. As a Stieltjes transform is just a trace of g over n. So as a first step, we want to show that m satisfies this equation. As a first step, I will show you how to show that actually at least its expectation is close to 0. So to do that, so you compute expectation of 1 plus dm. As the m is just a trace of g divided by n. This 1 is just a trace of the identity matrix divided by n. As an identity, you can write it use the definition of g, like h minus z times g. And then the minus g and minus zg and plus zg, they cancel with each other. So you get a trace of hg. And this is just the sum of hij times gji. And for this Gaussian orthogonal ensemble hij, they are all Gaussian variables. So to compute this guy, you can use the Gaussian integration by parts, or people sometimes also call it the Stein's lemma. Basically, for any Gaussian variable h, fh, so h is a Gaussian variable with mean 0. This is just the variance of h times the expectation of the derivative of h. Yeah, this is just integration by parts, but I think statisticians call it Stein's lemma, but Stein never discovered this one. So for this one, then use that equation. So the variance of hij is 1 plus delta ij over n. Then we get the derivative of hij of the Green's function gji. So for this derivative, you can compute explicitly because this is h minus z inverse. So the derivative of h minus z inverse is just the derivative with respect to h. I think, and then the indicator function ej plus ej plus ej. So this is those two, because this matrix H is symmetric, so the ij and ji's entries are both h ij. This is an indicator function such that ij's entry is 1 or the other entries is 0. So the derivative of gji is just gi. It's just there are two terms minus maybe gj. For the first one, just gji, and the second one is gjj, gii. So you plug in, just compute this one, and then you get this guy. If you believe me that it turns out the Green's function, only the diagonal entries, they are large. All those off-diagonal entries, gij square, they are pretty small. Then you just treat this as an error term and drop it. Then the sum of gii, gjj, this is just m square. So you get that expectation of 1 plus the m plus m square is close to 0. And the error term is really from this sum of those off-diagonal entries, gij square. Turns out it's pretty small in this case. And then this only gives you the expectation to show that 1 plus the m plus m square is small. We can use the same trick and compute the higher moment. Just compute this quantity to the power 2r and show this is small. And then use the Markov inequality. We can conclude that, in fact, the 1 plus the m plus m square is close to 0 with high probability. And then if we have a good control for the error, just take difference with this one. We can have m minus m semicircle is close to 0. And in the case close to the edge, we can have this error term, which is much smaller than 1 over n eta. Then in this way, we can conclude things like the largest eigenvalue is at most 2 plus something of order n to the minus 2/3. So for the de-Rigueur graph, we will try to mimic this argument to get the estimates for the Stieltjes transform. So for to repeat this process for random de-Rigueur graph. So for the first step, this is we need an equation for the semicircle Stieltjes transform for the semicircle distribution. We also have it for the Stieltjes transform for the Kerstin-McCain distribution. It's given by something like 1 plus d md plus d over d minus 1 md square and plus some more terms. So although it's not as nice as the quadratic one, but it's still some equation of md, although it's a power series. And the key thing is here, if d is much bigger than 1, if you look at those coefficients, it decays exponentially with the rate 1 over d, right? So you can somehow truncate this equation at some high order, then you will get only very small error. So you can truncate it and use that's a truncated equation. So the first step is not a problem. And for the second step, the key input is that the Gaussian integration by parts. So you can think this step is more or less like you resample the entry hij. Just resample it like use the Austin-Uhlenbeck process, which has a Gaussian distribution as a limit distribution. And this is just the generator for that dynamic. So this is basically you use some underlying symmetry of the Gaussian orthogonal ensemble. And to do that, in fact, we also have some symmetry for the. Yeah, we also have the symmetry for the random de-Rigueur graph, which is a pretty simple symmetry. It's called the simple switching. So it basically goes like this. It's very easy. You just take any two edges in the de-Rigueur graph, v1, v2, and v3, v4, and then you remove them and add the other two edges, v1, v4, and v2, v3. At least this preserves the degree, right? You still get a de-Rigueur graph. And if you just think for 1 minute, you will realize actually it also preserves the uniform distribution of the random de-Rigueur graph.
By the way, the numerics that you were quoting by those guys is done by sampling this way.
Oh, sampling this.
That's how they sample that's how they make their random de-Rigueur.
Yeah.
They start with anything and then they run this.
I see. Yes, because when I
So you don't need to go with some silly definition of what's the counting measure and so on. You just, it's very nice.
I see. I think another way you can also separate using the configuration model. Yeah.
This dynamics is exactly how they do it. It's known to be mixing very good.
Yeah. If you run this dynamic, every time you pick two edges as the switches from any deterministic de-Riegel graph, it will quickly converge to the uniform de-Riegel graph.
Gap of its own.
Yeah, this simple switching, it was first introduced by McKee to count the number of de-Riegel graphs. He can use this simple switching to get rid of self-loops or multi-edges. Then you can have a pretty precise counting for the number of de-Riegel graphs. So to use this simple switching, then we will, in fact, this simple switching will provide some discrete way to do the integration by parts. So we have the equation at the PZW at the MD satisfy this equation. Next step, we want to show that expectation of PZM. M is the Stieltjes transform of the empirical eigenvalue. It's also close to 0. So we compute the expectation of this guy. You get the trace of HG, and the trace of HG is just the sum of Aij times Gji. And because of our normalization, we divide by square root d minus 1. And then we separate the mean, because for the matrix A, each row sum is d, so expectation of each entry is d over n. So basically separate this d over n and subtract d over n. And because this A has the eigenvector 1, 1, 1, 1, 1, the Green's function G, it also has the eigenvector 1, 1, 1, 1. So you can compute this quantity precisely. It turns out it's pretty small, so you can ignore it. So next step is to compute this expectation. In the Gaussian case, we just do integration by part. But in this case, we will use that simple switching to do this integration by part.
You don't really have, you're using switching instead of integration by part, right?
Yeah, in switching plays a role as an integration by part.
Is the same that was done to prove local semicircle in the bulk?
Local semicircle.
In the bulk, so that
universality. Yeah. Yeah. So to do that for the edge Aij, we just introduce another edge IJKL. So Ij at the KL. So basically, if we have a graph A, it has an edge Ij at the K, IL and JK, then the condition it has this edge, then we can reseparate, replace it by A plus cosine IJKL. The cosine IJKL is just an indicator function. Adding those two edges as remove those two edges. So because the simple switching it preserves the underlying measure, so A at A plus cosine IJKL, they have the same law. So here we introduce the edge KL, rewrite this quantity as Aij times AKL, subtract AIL times AJK. This is just an identity because sum of KL is d times n. So we divide by d times n. So here this sum of IL JK is d times n squared, divided by d times n is d times n. Subtract d over n, sum over Ij, it's still d times n. So this is just some identity. And because that's A at A plus cosine IJKL, they have the same law. So basically, if you want to compute some function of A, condition that it has edge IJKL, you can think this matrix A is obtained in this way. You first sample A, which has these two edges, and then do a simple switching. So in this way, you get this should be the same as A plus cosine IJKL. At the time, the indicator function, it has the edge ILJK. So in this way, we can, any question for this equation? Then in this way, we can rewrite this quantity like the first term by AI. So this Aij, AKL, we can write it as AIL, AJK, and replace this times this by this guy. So again, we can then take out the leading term, replace AIL and AJK by d over n. And this guy, the difference is essentially the derivative of the Green's function in the direction of cosine ijkl. So you can compute the derivative, and still the leading order term is the diagonal entries. It gives you GII and GJJ over square root d minus 1. This is because in our normalization h is a over square root d minus 1. So this is really just the discrete analog for the Gaussian integration by part. And then this term, if you sum over ij, it gives you minus d over d minus 1 expectation m squared, which is the third term here. And of course, when you replace this AIL, AJK by d over n, you have some higher order terms. And for those higher order terms, they are all in the form of some product of the entry A times some product of the Green's function. You can repeatedly use this discrete integration by part to get higher and to get separate the leading term and get higher and higher order term. So in this way, you get that polynomial PZW. Yeah. So this.
You have to repeat this operation how many times?
You can just keep going. You get an infinite series, but for our setting, d is n to the epsilon. You can just truncate it as a finitely many terms. But even d is a large constant. This step, I think you can still do it, like truncate it at a degree like k is log n something. But what we have problem is, say by repeating this procedure, you get expectation of PZM is close to 0. But the next step is to show that the PZM is close to 0. We need to compute the high moment that p to the power 2r is close to 0. Then we can conclude that this PZM is close to 0. But to do this, to compute the high moment, we really need to show that the interaction terms between different copies of p, they are essentially 0. And it turns out, because this is a pretty long polynomial, there are so many of those terms. And what we in our current paper we can do is just expand this, and you get many terms, and then check these terms just by hand, one by one. And then show, all those terms, they are pretty small. They can be some error term, and we do it up to the order 1 over d to the power 3. And so our estimate is not very good. We only can get lambda 2, because the error of this guy is 1 over d to the 3. So we have this error is basically 1 over d to the 3. So finally, we only get lambda 2 is upper bounded by 2 plus something of 1 over d to the 3. And yeah, this depends on d, so we cannot go to very sparse. This is not good enough to show the Tracy-Widom for d is very small. And to get the optimal rigidity lambda 2 is less than 2 plus n to the minus 2/3. We may need some better understanding why those terms appearing in this expectation. They are all very small. But now we don't have a systematic way to understand it. So we maybe in the future I can say something more about this. But now what we do is just analyze those terms one by one. Yeah, and basically the last slide is just see there. Once you have that eigenvalue, largest eigenvalue, you have the location up to the order n to the minus 2/3. There's some pretty robust machinery you can do to show it's a Tracy-Widom distribution. So actually, the hardest part you need to prove the Tracy-Widom distribution is to show that the fluctuation of the eigenvalues is of order n to the minus 2/3. And maybe I can end here. And maybe with one things which puzzles me the most is for the d-regular graph, even for d is fixed, people still believe the Tracy-Widom distribution is true, or at least the fluctuation of the second largest eigenvalue is n to the minus 2/3. This you can see from the simulation, which is pretty precise. But if you think about the simple switching for the d-regular graph with constant d, so basically those entries, they are all of order 1. So when you do the simple switching, you change the location of the ones. That's a pretty large perturbation of the graph. There's no reason why so that will really lead to some order 1 change of those eigenvalues. But it turns out the fluctuation is very small, so this is very mysterious to me. Yeah, I can stop here. Thank you.
Why the fluctuation is small as it is, right?
Yeah, because if you do simple switching, actually from the perturbation point of view, you should have possibly have some order 1 change for the eigenvalues, because every time you change the entries by order 1.
They are intertwined.
Yeah, they are intertwined. Yeah, there must be some reason, but we didn't.
No way they are intertwined.
But for the second largest one, it can jump. But yeah, I agree. If you look at the third one, it's interlaced. But yeah. Thank you.